Hi, everyone. Hi, everyone. Welcome to the last session of POPL proper. So we have a session about proof assistance. And to start us with, we have a live talk by Rao about WebAssembly Mechanization, and he's also in job market. Take it away.
Thank you. Testing. All right, this works. So thank you, Druby, and good afternoon, everyone. My name is Rao, and I really thank you for staying until the end of the POPL to attend my talk, which is about a special design we named the Progressful interpreters, and about its application in our Wasm mechanization. So this is a joint work with Stefan, Radziuk, Conrad, and Philippa Gardner. So I'm actually going to start my talk by discussing a slightly different but still motivating method, talking about how to derive a sound interpreter from a constructive typed soundness proof. And along the way, I also recap some of the important concepts in type theory, which are also key components in our WasmCert-Coq. And it is only in the second part that I'll go to our progressful interpreter and discuss about its advantages. All right, so let's get straight to the foundation. Let us suppose that we are started with a relatively simple type system, which can be described by a binary typing relation between the set of expressions and set of types tau. And on the other hand, we have a small step operational semantics between the set of expressions. So it should be well known that the type soundness property is defined usually as two parts, including the preservation property and the progress property, where the preservation property would state that if you have a well-typed expression and if the expression steps to a new expression in the operational semantics, then the new expression has the same type as the old expression. Whereas the progress property states that starting from a well-typed expression, you can either take a step in the operational semantics and, or you know that your input expression is actually a terminal expression of the language. So getting to the interpreters, the one-step interpreter can be thought of really as a function that takes an input expression E and produces one of the several possible results, and including one of which being a successful execution result that returns a new expression E prime. And in our setting, we define the soundness of the interpreter to be a proof of the corresponding reduction term when the interpreter returns a successful step. So up to now, all of this have been mechanized in our prior work of mechanization of Wasm 1.0. So type system and operational semantics and proofs and etc. But this is not all of it, and we actually have more of the proofs and definitions and even more about talking about all different aspects of Wasm. So this is quite troublesome because Wasm is not something that is static. It is a kind of still actively evolving language. So whenever there is some kind of change in the underlying semantics, then that means we have to actually go to each of our different components and make sure that we are updating them in the right way, which is pretty inconvenient for us. So naturally, we are then thinking of a method of perhaps merging some of the components here into one. So it turns out that there's a particular resemblance between the progress property and a sound interpreter, in the sense that both of them take an expression E as an input, and in one of the cases, produce a new expression E prime and the corresponding proof term of the reduction relation. And this resemblance actually motivates the key idea of how to derive a sound interpreter from a constructive proof of progress and preservation. So to be more specific, let us suppose that we are started with a well-typed expression E of type tau. Given that the progress proof is constructive, which means that by Curry-Howard isomorphism, it can be think of as a really a computable progress function, we can apply it to the starting timing term and therefore obtain a new expression E prime as well as the corresponding proof term for the reduction. And the next important step is that we can actually apply the preservation property to the above two proof terms and construct a new proof term of the current expression E prime and its associated and the associating type tau. And in this fashion, our computation can basically continue indefinitely until, of course, if the progress proof decides to terminate us at some point. So I should really mention that this idea is not new. It's not invented by us, and this might have been folklore knowledge among experts in certain fields of type theory. But in our particular case, it came to us via a series of popularization by Phil Wadler a few years ago. So I have another side comment about the color scheme I'm using here, because on another day I was thinking about this, and I found that there's a clever, not clever, there's a tricky resemblance between this and a typical CMYK printer, because that's how the printer does its job. It doesn't carry the green ink, but it rather prints the green color by mixing the cyan and yellow. All right. So all of this sounds good so far, and we went on and implemented this method on top of our mechanization. So the short story is that it works to some extent and with additional efforts. But we found out that there are actually quite a lot of limitations to this method. The first one really is that if you are really counting on the type soundness proof to do the execution for you, then you are having the issue when you are trying to extract the proof, or the interpreter, from the proof assistance to a language like OCaml, because these proof terms can now not be erased during execution. So this is quite unfortunate for the interpreter, because it means that you are carrying a much larger runtime representation, which slows it down by quite a bit. So in fact, in our experiment, we found out that there is actually a complexity level inefficiency, which is displayed by the benchmark here. The benchmark basically is on a very simple Wasm program evaluating the values of the Fibonacci numbers by a very simple linear loops. So supposedly it should have a linear complexity. But what we found is that the type soundness interpreter actually demonstrates exactly a quadratic behavior, which is quite interesting on its own. So we went on and investigated what the source of this problem is. And it turns out that there's a explosion of growth in the sizes of the proof terms. And it is due to a specific interaction between some of Wasm's typing rules and our existing type soundness proof. So naturally, we then went on to try to see if we can actually solve this problem. The answer is yes, but it is also very difficult to do that, because in this structure, when you are trying to optimize the interpreter, you are necessarily dealing with the proofs. And the second point, which is more important, is that the changes required are actually really awkward, and in some cases just plain stupid, if you view it from a perspective of doing a proof. But anyway, in the end, we found out that the type soundness interpreter can be optimized to linear complexity, although it is somewhere around 70 times slower than the original one. The key takeaway here is that even a subtle difference in the proof structure can have a great impact on the speed of the interpreter, which is something that you certainly don't want to care about when you're writing the type soundness proof, which is already quite tedious. And the last limitation, which is slightly non-obvious, is that this method actually requires a separate function to get you started, because in real world, you don't actually have programs with the complete proof terms of the typing judgment for you. And you have to construct that by doing a type checker or something like that by yourself. And we know that this is generally a difficult problem for programming languages and can be undecidable for certain languages. And we know that a mere type annotation is insufficient for our purpose, because the type soundness proof actually requires the concrete typing terms instead of just a type annotation to run. But fortunately for our case, this can be done for Wasm because of the existence of a validation algorithm, which, although in the end it did require additional work by doing some more correctness proofs on our side. So these limitations really mean that we shouldn't be doing this method for the long term. And in the end, so after that, we are trying to see if we can view the problem from the other direction, which means that instead of trying to generate programs from proofs, can we write programs that carry the proofs? And this is where the progressful interpreters come in. So let us start by revisiting the traditional structure of a one-step interpreter, which is as described previously. It is a very well-known method in several books and many places, that you can attach a certification of correctness to certain branches of execution, so that you are getting a dependent typed functions and which certify its own correctness. So what is the most important part of our progressful interpreter is that being motivated by this method, we similarly augment the other cases of execution by a similar certification. So for the case where the interpreter terminates, we require a proof that the input is actually terminal. And the key point here is that for the case where the interpreter wants to crash, we actually require a proof that the input expression is malformed. And to be more concrete, we define it as it cannot be associated to any type of language. So what good does this particular crash certification does? It turns out that if you do it via a contrapositive argument, then this specific structure induces a progress proof for free. Because suppose if you now started with a well-typed program, then by applying the progressful interpreter to the program, you would know that you can never land into the crash case. And as a result, you're either getting a successful reduction or a terminal result, which is precisely what the progress property states. Another thing to mention, to note here is that this progressful interpreter provides a guarantee that is stronger than the original soundness, because now any valid input has to actually make a progress. All right, so this is about the abstract structure. Let's look at how it is actually done in like the WasmCert mechanization. So I'm showing a kind of like simplified structure of the one-step interpreter here, which is like, to be honest, like quite similar to the abstract version I've shown earlier. So we have a fixed point of a one-step interpreter taking the different components which form the WASM configuration, and it returns one of the several results, which includes the previous three, but plus a bit more to deal with WASM's control flow, which we'll omit here. The progressful interpreter, as promised, augments the type of the return type to a dependent type, and as a result, attach a certification to each of the case of the execution results. All right, so we have successfully implemented the progressful interpreter on top of our old WASM 1.0's work. And the next question is, can we actually do more work on top of that? Because recall that our original purpose was to maintain the mechanization. So the first thing we tried is to implement an optimized runtime representation, and this is an idea from the Isabel counterpart of the mechanization, which targets at evaluation context. The result is that we get an interpreter which is vastly faster on programs with heavy control flow or function calls. And incidentally, it actually produces a smaller code base because the way that the control flow are dealt with is simplified. And the second significant part of our work is that we have updated the underlying semantics to the much larger WASM 2.0 feature sets. And of course, now this is in our subjective experience, but we found out that the process of updating the interpreter was fairly easy. And in the process, we have also found and fixed several errors in the official specification. Right, so it's time to display some benchmarks for the optimization. So this is a slightly different benchmark that similarly computes the Fibonacci values, but it is done in a way that via function calls, recursive function calls. So which means that no intermediate values are remembered, which means that this program will involve quite a lot of like function calls and returns. So as expected, the type soundness interpreters, being like optimized or not, are the slowest ones, which are actually even like around 3 orders of magnitude slower than the WASM's reference interpreter. And next in line are our progressful interpreter and the Isabel counterpart from Watt. And they actually have similar performance for our optimization target. And for the sake of completeness, we have also like tested the industrial runtime, which is named WASM time by Bytecode Alliance, and it is around 2 orders of magnitude faster than either of the optimized interpreter from proof assistance. But we hope that this is kind of expected. All right, so reaching the end of my talk, I want to quickly describe 2 related approaches to our work. So the first one is the use of an intrinsic typed representation, which means that the programs themselves carry their types with them. And we know that the distinction between the type soundness interpreter and our Progressful interpreter is pretty big in our setting, because Wasm has a extrinsically typed semantics. And in the other case of intrinsically typed semantics, then a proof of progress would actually be quite similar to a interpreter itself. And but do not forget that there's a similar issue of how to get this initial timing term, even if you are using the intrinsic type representation. And the second related approach is the use of definitional interpreters, which means the use of an interpreter as the normative definition of operational semantics, which certainly helps to cut away this, even the operational semantics from the mechanization. But this really doesn't help our purpose, because in the end, our mechanization is supposed to reflect Wasm's official semantics. So if we cut away the only connection, then we are losing the trust of our mechanization here. And another point is that this method also only works conveniently for a completely deterministic semantics, which Wasm is unfortunately not. All right, so to conclude my talk, I'll give a summary of what we have done in this work. We have, to our knowledge, for the first time, we have implemented an end-to-end progress and preservation interpreter for a real-world language Wasm. And we have also investigated the source of its efficiency and tried to perform some optimization on that, which doesn't work. And the second is that we have proposed this method of Progressful interpreters and implemented for Wasm WasmCert 1.0. And on top of that, we have performed some optimizations and updated the semantics to Wasm 2.0 and correcting some errors on the way. So this concludes my talk, and thank you again. I'm happy to take questions now.
Well, we thank the speaker and open the floor for questions.
Thanks for the nice talk. Yeah, so this idea of delaying the type checking to runtime, that's very nice. So if I'm in a situation where I did do the check already in a different stage, is it possible to, you see a way to basically optimize your interpreter to remove those branches?
I don't think this is really possible because, well, if you are sticking with the type soundness approach, then there's no way you can really like escape from having to use the typing term, because like if essentially like the process of that execution is like interleaving progress and preservation, and you are producing a new kind of like proof term at each step. So having a initial one doesn't like help coming up with the doesn't help you immediately get to the next ones.
Any other questions?
I have not understood what is your initial definition of the semantics of this WebAssembly. You have a little row here. How is it defined?
Sorry,
from
which
E
one?
to E prime. That looks like a transition semantics.
Ah, yes. So
and how is it defined?
Yes. So in the formal semantics of Wasm on their website, this is defined as like basically a small steps relation. And in our work, in our mechanization, this is captured by like basically a line-by-line corresponding inductively defined relation in ROC.
And you cannot extract an efficient interpreter out of these semantics?
Well, an inductive relation itself is not executable, right? So the other way is certainly possible. And like as I said, like another issue with Wasm is that the semantics is not really deterministic. So so you have to choose a branch to go like when there's a divergence.
Okay.
Let's thank the speaker once again.